So now we'll take a look at method 2, which is still going to involve us putting these vectors into a matrix A. In this case, we'll make it a homogeneous system instead, although we kind of know what the results are here, so we could probably get away with leaving this off and just row reducing the matrix anyway. So we've got our homogeneous system. Again, what we're looking for is whether or not the solution is the trivial one. So we row reduce the matrix and see what happens. When we do that, again, RR, EF. Now in this case, we just row reduce the matrix A. Again, I've already done this. We would get 1, 0, 0, 0, 0, 1, 0, 0, minus 2, 3, 0, 0, 0, 0, 1, 0, and 1, 2, minus 1, 0. Of course, our column of zeros for the homogeneous system. So you can see here that we do get some free variables in here, so it's not the trivial solution, which means that these are linearly dependent, which is not a surprise. We got 5 vectors out of R4. We know at least one of them is linearly dependent on the others. The trick for us is to identify what are sometimes referred to as the pivots, which we in this class have talked about as sort of leading ones. So I have a leading one here, here, and here, and no leading ones in columns 3 and columns 5. And what that means to us is that we would delete columns 3 and 5 from our original set, or if we were to look up here, we would delete columns 3 and 5, and these columns that have the pivots in them, these leading ones on 1, 2, and 4 are the ones that we keep as part of our basis. So these vectors here, 1, 2, and 4, become the vectors in our basis. So just writing that out, under this method, our basis is equal to the vectors 1, 1, 2, negative 1, 1, 2, 1, 1, and column 4, which is 1, 0, 4, negative 1. Those are the ones that we keep. Again, that's associated with these leading ones, or what are referred to as pivots. So that gets us a basis. Again, the benefit of this is that it actually maintains the same coordinate system. Sometimes we care, sometimes we don't care.